begin by looking at something that we know. So this is essentially math 2A, so or calculus 1, and this is calculus 2. So this is what we are doing, math 5B. So this is one variable calculus, and essentially what we study in calculus is we study functions. And one of the basic operations you can do in a function is to compute derivative. To compute derivative, well, but the function might have more than just one variable. So you also want to compute partial derivative. And the key point is the main application of derivative. So derivative essentially is the same as slope. Derivative is essentially the same as slope. And the main application of derivative is essentially derivative is used for the process of linearization of the function. So here's a function f, here is a function f, and maybe the function is difficult, and maybe from application point of view, you only want to know what the function looks like in some neighborhood of some given point, x0. Then this is the linearization, and really the function is very, very similar to the given function f as long as you stay close to this point x0. Okay, so what's the equation of this line L? So if this is point, if we call this point x0, then what is f prime of x0? F prime of x0, that's the slope of the tangent line to the graph of this function at this specific point. So when you look at this function y equals f of x0 times x, how does this function look like? Well, this function will go through 0, and essentially that's this function. And essentially that would be this function. This is the function y. This is the function. This is the function y equals f prime of x0, f prime of x0 times x. Okay, so now the next thing what you want to do, you want to shift this function to the right. So now you consider a new function, maybe y equals f prime of x0, and then times x minus x0. How does this function look like? That's the slope is the same, but the slope is the same, but the function goes through this given point x0. This function goes through this given point x0, and all you have to do, the last thing you have to do, you want to shift this function all the way up to the point of interest, which is f of x0. So now consider the function exactly this one plus f of x0. So let me just rewrite the same thing. So f of x0, and then plus this portion of this function. So f prime of x0 times x minus x0. This is exactly the function that we want to. That's the linearization of this function f, because what you do, you take this function, and you shift this function a few units up to the given point. So that's the function L, and this is the linearization. That's the function L of x equals that. Okay, this is something what we know, and this is the one variable calculus. But now we want to develop a similar formula for not a line, but the tangent plane. This tangent plane is supposed to be tangent to the given surface. So let's say that the surface is given, so f of xy, f of here was f of x. That was just a function of one variable. Now let's say that we have a function f of xy, and let's say we have one point of interest in the domain of this function, and maybe that's this point. And let's say the first coordinate of this point is x0. So we have a given point. This point was just one coordinate in this situation because that's just a one-dimensional case. But now let's go to two dimensions. So this is R1. This is one-dimensional case. But now let's go to two-dimensional space. And now my domain is a subset of a two-dimensional space. And let's take one point of interest, this one. This is this point x0, y0. See, I have two components because I am now in two-dimensional space. And now I want to find the linearization of this function close to this given point. So what we do is we look at the derivative of this function f at this specific point x0, but now derivative here, derivative is with respect to x and with respect to y. So I'll look at the derivative of this function f at this specific point x0, comma y0. This is just one component of this derivative. The other one is with respect to y. So f, the partial derivative with respect to y of this function f at the same point x0, comma y0. So essentially, see, this is the f of x0. This is the number. This is a slope, except that slope here is a vector. Okay. Now I'm going to take the dot product. What we did here, this is the one-dimensional dot product, which is the same as multiplication. But now I'm going to multiply this by this vector x minus x0, y minus x0, x minus x0, and then y minus y0. Okay, and what I want to do is I want to take this plane now and shift this plane up to this given point of interest. So I'm going to add to this the point f of x0, y of x0, x0, comma y0. And this is exactly L of xy. This is exactly L of xy. So this is the linearization of this function f at this point x0. Okay, so my handwriting is not that great, so let me just say again. That was the function f, and this is the one-dimensional case. I won't be writing anything, but that was the one-dimensional case. That was the function f. The key point of derivation, derivative, is to be able to find this linearization. And derivative is essentially this slope at a given point. So the function f is given, compute f prime, and evaluate f prime at this point x0. That will give me this number, f prime of x0. What is this? That's the slope of this line. Now shift this function to the right by adding this factor x minus x0. And lastly, what to do, push this function appropriately many units up by adding this number f of x0. This is the function L. That's the linearization of this function f. And this is the tangent line to the graph of this function at this point x0. So let's do an analog of this in two-dimensional case. So we just mentioned this. You take a function f of xy, f of xy, and now I can compute, well, two things. I can compute derivative of this function f with respect to x is a function of xy as well. And as also I can compute derivative of this function with respect to y, those two things. Okay, so given a function, given a function f of xy, I can compute the x derivative of this function and also the y derivative of this function. So this new function is a function of x and y, and so is the y derivative. It's a function of x and y. Now evaluate this function at this given point x0, y0. So we get a number. If I look at the partial derivative of this function f with respect to x, and when I evaluate this function at this point x0, comma y0, this is a number. And also, I can do the same thing with the other function. I can take the partial derivative of this function f with respect to y, and I can evaluate this function at this point x0, comma y0, and that will give me a number. That will give me a number. So now I can look at the vector. This is the partial derivative of this function f with respect to x at this point x0, comma y0. That's the first component of this vector. And the second one is exactly the other number. So this is the partial derivative of this function f with respect to y at this point x0, comma y0. Okay, this is the vector. We know that what is the dot product? So if I take another vector, which is x minus x0, x minus x0. So this vector is responsible for the translation, and then y minus y0, y minus y0. And then I have this plane, essentially I have this plane, but all I have to do with this plane now is I have to push this plane up to the point of interest. And formally, so this is the dot product. This is the dot product. This is the dot product of two vectors. And to this vector, I'm going to add another vector, which is f of x0, x0, comma, y0. Okay, so notice that this is a function of two variables, x and y. This is a function of two variables, x and y. And let me call this function L of xy. And this is exactly the linearization of this function f at this point x0, y0. And this is the tangent plane to the graph of this function of two variables. Okay, so this is exactly the formula. This is the vector of partial derivatives. This is the partial derivative with respect to x at this point x0, y0. The other component of this vector is the partial derivative of this function f with respect to y at this point x0, y0. And this is the dot product. And then the other vector is x minus x0, y minus y0. And then what I have to do is I have to push this plane up to this point of interest, which is f of x0, comma, y0. And let me call this function L of xy. And the textbook use L because this function can be thought as a linearization, local linearization of the surface. So now what we know, what does it mean? Okay, this is the dot product. This is the dot product. How do we multiply two vectors? I'm going to take the first component of this vector, multiply times the first component of this vector, and then I'll take the second component of this one, multiply by the second component of the other one. Okay, so now if we multiply, this is what I did here. This is just a multiplication. This vector times this vector, that will give me this. And this is exactly the linearization. This function sometimes is called this function, sometimes it's called the linearization. The linearization of this given function f at this specific point x0, y0. Okay, so example, let's say that the function I want to find the linearization is this one, z equals 2x squared plus this one. And I want to find this linearization at this point 1, 1, 3. So let me show you on the picture what we have to do. So here's the function 2x squared plus y squared. This is the function, looks like this. Essentially, it's like almost like a parabola, but in three-dimensional space. This surface lays in a three-dimensional space. And the function looks like this. So let me take this point 1, 1. So here's x, y, z. So if x is 1, this is the x-axis. So this is x equals 1. This would be y equals 1. So this point is just about, well, just about that's the point. And let's now go all the way up to the function. So all the way up to the function. So here's the point of interest. I want to find the linearization of this function at this point. So what I have to do, let's say the function f of xy, the function f of xy is equal to 2x squared, 2x squared plus y squared. This is the function of two variables. So it really is a surface in a three-dimensional space. It's a function of two variables, x and y. Let's compute the partial derivative of this function f with respect to x. What would be this? Partial derivative of this function with respect to x. Excellent, this is for x. And let's compute the partial derivative of this function. Well, I don't I don't use the prime notation, but let's compute the partial derivative of this function f, but now with respect to y of xy. Okay, I'm going to ask you also this question. What is the partial derivative of this function with respect to y now?
y.
Excellent. To y. Okay, so now let's look at this partial derivative of this function f, but now at this point of interest at 1, 1. So at 1, 1. Well, this is obviously, what is this function at 1, 1 equals to? 4 times 1. Okay, so that will give you 4. And let's compute the partial derivative of this function, but now at this specific point of interest at 1, 1. Okay, what is this function at 1, 1?
2.
Excellent. 2 times 1 is 2. Okay, so now let's look at the vector of partial derivatives. So I'm going to have 4, and then I'm going to have 2. Okay, this is the vector of partial derivatives. And then times, the other vector would be x minus x0. So x minus, well, x0 is just 1. So x minus 1. And then y minus y0. So y minus what point? Y minus 1. Okay, and last thing to do, I have this is, see, this is exactly the plane. But what I have to do is I have to shift this plane to this point of interest. So I have to add to this f of 1, 1. 1, 1. Okay, so what is f of 1, 1? Let's see. This is 2 times 1 and plus this is 3. So the linearization L of xy, L of xy is equal to 3. This is L of 1, excuse me, f of 1, 1. See, f of 1, 1 is, let's see, f of 1, 1. Let's see, 2 times 1 squared plus y is also 1, so 1 squared. So this is 2 times 1 plus 1, because 1 squared is 1. So this is 2 times 1 is 2 plus 1. Okay, so this is equal to 3. So this is f of 1, 1. So this is 3. And now I have the inner product, or the dot product. So this is 4 plus 4 times x minus 1. And then plus 2 times y minus 1. 2 times y minus 1. Okay, and simplify this a little bit, and so that will give me 3 plus, let's say, 4x, and then 4 times negative 1, so negative 4, and then plus 2 times y, and negative 2. So that will give me, let's say, this is 4x, and then plus 2y, plus 2y, and then, okay, what's the constant? So this is 3, negative 4, and negative 2, so it's negative 3. Negative 3. Okay, so the equation of this plane is L of xy, L of xy equals 4x plus 2y, and then minus 3. Okay, and we are done. That's the linearization of this function at the specific point 1, 1. Okay, so let me just show you again. My handwriting is not very good one, but let me now show you in a. Okay, so what we did was, first of all, we have computed the partial derivative of this function with respect to x, and then we have evaluated this function at this point 1, 1. So that will give me 4. Now the same thing, we have computed the partial derivative, but this time with respect to y, that's a function to y. And then what we did, we have evaluated this function at 1, 1, that will give me 2. Are there some people in the waiting room? Yes. Okay. Exactly. Okay, thank you for letting me know. I have just admitted those people in the waiting room. Yeah, perfect, thank you. So now this is the what partial derivative of this function with respect to y, that's 2y, and then evaluate this function at 1, 1, that's 2. Okay, now what we have to do is we have to look at the vector of partial derivatives at 1, 1. So this is the partial derivative of my function with respect to x, partial derivative of the mass function with respect to y, both evaluated at 1, 1. This is one vector, and this is the dot product. The other vector is x minus x0, so x minus 1, and then y minus y0, so y minus 1. In my example, we know this is the dot product. This is the dot product of two vectors, so we know how to evaluate, how to multiply two vectors. And then what I have to do is I have to shift this plane to the point of interest by adding f of 1, 1. So this is exactly L of x1. So when we simplify this, f of 1, 1, this is 3. f x1, 1, this is 4. And then the other derivative at 1, 1 is 2. And then I have, this is inner product of those two vectors. This vector inner product times the other vector, which is x minus 1 and y minus 1. So this is going to be equal 3 plus this is, how do we multiply the dot product? This is 4 times x minus 1, 4 times x minus 1, and plus 2 times y minus 1, 2 times y minus 1. So this is going to be equal to 3 plus this is 4x, and then minus 4, and then plus 2y, and then minus 2. Okay, so this is going to be 4x plus 2y plus 2y. And let's see, this is 3, negative 4, and negative 2, negative 3. Okay, negative 3. So this is the equation of this plane. The equation of this plane is 4x plus 2y minus 3. This is exactly the linearization of this plane at this specific point. And what does this mean is, well, okay, so I don't want to say that. So now let me say very quickly a few words about, because when we have partial derivative, let's say function of one variable. So function f is given. Let's say that maybe the function looks like this, and then something like that. It's a function f. And let's say I have some point, maybe in the domain of this function, I have some point x0. So how do we think of, what's the interpretation of f prime, or derivative of this function f, at x0? This is slope of this of the tangent line. So we take this is the point, and then we take the tangent line to the graph of this function, and this number f prime of x0, this is exactly the slope. So when you look at this function y equals, let's say, for example, the slope was maybe negative 2, for example. Then if you look at this function negative 2 times x, well, that's this function. So we know to get to this function, first of all, you need to shift this function to the right and then push this function up. Okay, so the interpretation of derivative is slope. Interpretation of derivative is slope. Now, how to think of partial derivatives? How to think of those two numbers? Because if I have this function f of xy equals 9 minus x squared minus y squared, here's the graph of this function. And how to think of, well, I can compute partial derivative of this function f, partial derivative of this function y with respect to y, and how to think of the partial derivative. So like again, the function was this one. That was the function f. 9 minus x squared minus y squared. And let's take y to be equal to 1, for example. Okay, let's take the function, this function f. The graph is shown here. And let's take this point y equals 1. You know, for example, just for 1 second, let's take this point y is equal to 1. Then I have this function f of x1. Let's see how what this function is equal to. This is going to be 9 minus x squared and then minus 1. So this is going to be 9 minus 1, which is 8 minus x squared. Okay, so now I have a function of one variable. The function is simply 8 minus x squared. Well, if this is the case, if this is a function, this is the function 8 minus x squared. And notice that this is a function of one variable. So the function looks like this. This is the plane, this is the plane. This is the plane y equals 1. So here's 1 on the y coordinate, and this is the plane y equals 1. And if I do the intersection of this plane and the function, that will give me now this function of one variable. See, this is a function of one variable. This function is exactly a function of one variable. So this function, that's exactly the function y equals, well, 8 minus x squared. 8 minus x squared. So if I want to compute the derivative of this function, then I know this is, of course, this is negative 2x. So the partial derivative of this function f with respect to x is when we fix one of the two variables, then we have really a function of one variable, and then we compute the derivative of this function. Now, when I evaluate, let's say I pick some point, maybe x0, and then, or maybe y was 1. Okay, so x0, 1, and maybe this point x0 is over here. So I have this point x0, 1. Let's go all the way up to this function. So what is this tangent line? This is the slope. So if I compute partial derivative of this function f with respect to x is a function of two variables, x and y. So this function is equal to negative 2x. But when I look at, when I evaluate this function at this point, so partial derivative of this function f with respect to x at this point x0, comma 1, this is exactly, well, negative 2 times x0. And the interpretation of this number is that's the slope. That's the slope. So that's the slope. So again, when I have a function of two variables, f of x, y, well, then I can compute derivative of this function with respect to x, partial derivative of this function with respect to x, and then I can evaluate this function at a specific point. Maybe this point is x0. So for example, this is the point x0, and this is 1. So the point in the domain of this function is about this point. And then if I go all the way up to the function, that will give me the slope. Okay, so partial derivative is simply the same thing as derivative, but with respect to one variable, and also interpretation of it is also slope. But slope of this line along the x-axis. The partial derivative of with respect to y, exactly the same interpretation. So I can compute derivative of this function f with respect to y. Derivative of this function with respect to y, this is also a function of two variables, x and y. And then I can evaluate this function at a specific point. So let's say maybe I'll take some plane in the domain of this function. Let's say, for example, something like this and something like this. Okay, and then maybe something like this and something like that. Maybe I'm not sure how to draw this exactly, but something like this. Then derivative of this function f with respect to y at a specific point x0, y0, This is the slope of the other line. This is the slope of the other line. This is the slope of the other line. That's the interpretation. That's the geometric interpretation of partial derivatives. Not that important, but just something to have to support your intuition on when you are thinking of partial derivatives. So in one-dimensional partial derivative, in one dimension, partial derivative is slow. But then in two dimension is also slow, but too slow, so to say. And that's why you have the vector, because slope with respect to the x line and slope with respect to the y line. Okay, so very quick example, how to compute partial derivative. I think we mentioned this the example the other day, so I don't want to spend that much time on this one. So function f is given, then I can compute the derivative of the function with respect to x and with respect to y. So, okay, we did this the other day. So derivative of this function f with respect to x is a function of x and y as well. So derivative of sine is cosine, and then I'm using the chain rule, and I'm multiplying this by derivative of this inside function, but with respect to x. Well, so derivative of this function is 1 divided by that. Another notation for this partial derivative, and our textbook used both. So our textbook used either this notation for partial derivative, or they would also use this notation. This is the partial derivative of my function f with respect to x at a specific point xy. And the same thing, partial derivative of my function with respect to y, that would be cosine of this function times derivative now of this function, but now with respect to y. So that's the function. Another notation for this function is f. This is the partial derivative of f with respect to y, and it's a function of x and y. Okay, so that was sometimes they call this the first partial derivatives, but notice one thing. This is also a function of two variables. This is also a function of two variables. And if so, then you can take this function fx, you can take this function of x, and you can compute, so you can take this function of x 2 times, a copy of it, because it's a function of x and y, then you can compute derivative of this function with respect to x, or derivative of this function with respect to y. And that will give you this, those are known as the second partial derivatives. Exactly the same thing here. This is a function of x and y. Well, this is the partial derivative of this function f with respect to y, but it is a function of x and y. And if this is a function of x and y, so you can take a copy of this function 2 times. So fy and fy is a function of x and y. So you can compute derivative of this function with respect to x and derivative of this function with respect to y. So you can look at the matrix. This is this derivative xx, derivative xy, and then derivative, that would be yx, and then derivative yy. That would be the matrix of partial derivatives. We won't be doing this, so absolutely don't worry about matrices. Just wanted to mention that often they use. But the thing is that if this function f is nice and continuous one, then the mixed partial derivative are the same. This partial derivative is the same as that one. So what it means is that the matrix would be symmetric. So here's an example of a set of a partial derivatives. Okay. Let me see. On the previous slide. This one? Okay. So let me see. Well, let's compute the first one. Let's say df dx of xy Okay, and this is my function is compute derivative. So first of all, this is the function sine. Derivative of sine is cosine. So I have cosine of, well, whatever we have in this function. So we have x divided by 1 plus y. And then I'm using the chain rule. I have to take this function, the inside function, which is x divided by 1 plus y. And I have to compute derivative of this function with respect to x. So I have to compute derivative of this function with respect to x. So this. Okay, so this is cosine of this function, cosine of this function, x divided by 1 plus y. And then let's see. Well, okay, let's see. What's the derivative of this function with respect to x? Let me just write this function again. So the function is x divided by 1 plus y. Okay, I can also write this function as 1 divided by 1 plus y times x. So if I want to compute derivative of this function with respect to x, that would be derivative of this function with respect to x. But if this is with respect to x, then this is a constant. So this is 1 divided by 1 plus y. And derivative of x is 1. So we have 1 divided by 1 plus 1. Okay, and the other one, exactly, and the other one the same. So if I want to compute derivative of this function f with respect to y of xy, this is going to be equal the same thing. Derivative of sine is cosine. Derivative of sine is cosine of whatever the input is, x divided by 1 plus y. Okay, and now I have to take the inside function, which is x divided by 1 plus y. And I want to compute derivative of this function with respect to y. Derivative of this function with respect to y. Okay, so this is going to be equal cosine. This is going to be equal cosine of x divided by 1 plus y times, okay, now let's think of this. Let's think of this. What is the derivative of this function with respect to y? Okay, so maybe we can do this aside. Okay, so let me remind you something. F divided by G from calculus method A. If I want, okay, two things. First of all, the product rule, F times G. If I have to compute derivative of the product, this is derivative of the first function F times G plus derivative, well, plus the first function F times derivative of this function G. This is the product rule. And what is the quotient rule? Because for that, we'll be using the quotient. So this is going to be equal derivative of the first function times G minus derivative, the first function times derivative of the second function divided by G squared. Okay, so this is the product rule. This is the product rule, and this is the quotient rule. This is the quotient rule. So now let's take this function. Now let's take this function, and I want to compute derivative with respect to y of this function x divided by 1 plus y. 1 plus y. Okay, so I'm using quotient rule. I'm taking derivative of this with respect to y. Okay, so derivative of x with respect to y is 0 times this, so this is going to be 0, and then minus the first function, which is x, times derivative of the denominator with respect to y. Okay, let me ask you this question. What is the derivative of this denominator 1 plus y with respect to y?
1.
Excellent. Yes, it is 1. This is excellent. Nice. Divided by, and then what I have to do is I have to take g squared. So the function 1 plus y squared. Okay, so this is going to be equal negative x divided by 1 plus y squared. Okay, so this is the negative, this one is right here, and this is x divided by 1 plus y squared. Yes, thank you. Oh, you're most welcome, and thank you for asking, because maybe second partial derivatives is essentially, let me see. Okay, so no time. Second partial derivative is we have a function f of xy. Well, if I have function of f of xy, then I can compute the x derivative of this function, but also I can compute the y derivative, the partial derivative with respect to y. That will give me a new function of x and y. So this is the partial derivative of my function f with respect to x, and this is the partial derivative of my function f with respect to y. And notice one thing, well, obviously this is a function of two variables, x and y. So I can also compute the derivative of this function with respect to x. And the derivative of this function with respect to y. Okay, so that will give me fxx. That will give me fxy. Okay, and it's exactly the same thing. Since this is a function of x and y, then I can compute the derivative of this function with respect to x and also with respect to y. So that will give me fyx, fyx, and that will give me fyy, fyy. And notice one thing, fyx is 6xy squared, and so is this one. So the mixed partial derivatives are almost always the same, but not always. They might not be the same, you know, where they might not be the same when the function was a discontinuous, the derivatives were discontinuous as well. But when the derivatives and the function itself are nice and smooth and continuous, then we also always have the case that the mixed partial derivatives are the same. So that's why when you look at the matrix of partial derivatives, so fxx, fxy, and then fyx, and then fyy. Okay, so how the matrix looks like in this example? Well, in this example, this is fxx, 6x plus 2y cubed, 6x plus 2y cubed. Okay, and here's another element of this matrix. I have no time to write all of them, but you will see that this matrix is symmetric, meaning that this and this are the same.